Hello everyone. In this video, I'm going to demystify the inclusion exclusion principle. This principle is widely used in many counting problems. It's a very powerful tool for solving many combinatorial problems. So let's deep dive into this problem and see why works and why this is true. And let's deep dive. So the inclusion exclusion principle tells about the cardinality of a union of number of finite sets. In this video I'm talking about only finite sets. Okay, there is no infinite sets. Okay, we are not dealing with cardinality of infinite sets for contours, all those definitions. We are dealing with infinite sets. Here cardinality of a, this mod of a means the cardinality of a. This means nothing but the number of elements in the set a. Since a is finite, so number of elements must be some natural numbers. So this is what the cardinality of A means. The number of elements in the set A. That's it. So the inclusion exclusion principle says for the basic case for two sets, the number of elements in A union B is equal to the number of elements in A plus the number of elements in B minus the number of elements in A intersection B. Remember, this double bar sign means the number of elements, which is also known as cardinality. So the number of elements in A plus the number of elements in B minus the number of elements in both. Now, you all know this from school days. This can be shown by Venn diagram also. Like this, the common part is counted twice. So we deduct it once, and just to balance it, it's also counted once. But let's see why it is true in another way. The main theme in counting the number of elements in a set is that each and every element must be counted exactly once, not twice, not thrice, neither zero times nor minus one times, exactly once. We don't want, do you want any element to be counted repeated times? That will be over counting. And if you are not counting some elements, then it is called under counting. We don't won't want over counting or under counting. We want each and every element must be counted exactly once. So let's see how here the each and every element is counted exactly once here. See, the elements which are present only in A but not in B, those are counted here once only. The elements which are present only in A, that are only counted here only. Those will not be counted here since it is not present in B. And those will not, also not be counted here because those elements are not present in both. So those elements which are present only in A is counted once here only. And similarly, the elements which are present only in B but not in A are counted here once. Okay, so we all get this. But what about those which are present in both? Those which are present in both are counted here once. So it is counted twice. So there is a double counting. So we have to balance it. So here it is deducted once. So 1 plus 1 minus 1 is equal to 1. See, there are three cases only. Either it is present only in A, either it is present only in B, either it is present in both. All those three cases, each and every element is counted exactly once only. So the inclusion exclusion principle for two sets, yeah, this is true. Now let's move on to the next one, which is the inclusion exclusion principle for three sets. For three sets, this is the number of elements in A union B union C. Here it is the number of elements in A plus the number of elements in B plus the number of elements in C minus the number of elements in A and B minus the number of elements in B and C minus the number of elements in C and A plus the number of elements in all three. See, we will also split this into two types of cases. The elements which are present in exactly one of those three sets, exactly once, not two. Those are counted here only once in this. If it is present only in A, it is counted only here only and no other else because it is not present in both, only in A. Those which are present only in B, those are counted here once and nowhere else. No reduction, no, only here. And those which are present only in C, similarly are present here only. And what about those which are present in both A and B, but not in C? Only two of the ABCs, not any other, nowhere else. So which are present only in A and B, those are counted here once, here once. It is not present here. Okay, it is present here. It is not present here. It is not present here. It is not present here because the I am talking about those elements which are present only in A and B and nowhere else. Only A and B. So here it is counted here. It is counted here. It is zero times counted. Here one time it is deducted. So it is also 1 plus 1 minus 1. So similarly, it will be 1. Similarly, for those which are present only in B and C but not in A, and C and A but not in B are also counted once. Now, the most interesting is this one. It is present in all three. See, those which are present in all three, how many times those are counted? So, since these elements are present in all three, it is counted here once, here also present, 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 and here also present. So how many times it is counted and deducted? See, 1 plus 1 plus 1 minus 1 minus 1 minus 1 plus 1. So these are 0. 1 plus 3 minus 3, 0 plus 1 is equal to 1. See? So here also each and every element is counted exactly once only. So I guess if there are four sets for A union, B union, C, the number of elements, you can similarly say. I hope you all know how to write the pattern, right? It's nothing difficult. Just take the cardinalities of those taking single at a time, that is AIs, I running from 1 to n. This is only taking the cardinalities of one at a time. Then I deduct by taking two different sets and intersecting them. This is how I and needless to say, I and j belongs to 1 to n. Okay, where the number of sets are n. This is just A1 union A2 union up to AN. Okay, this is the most general case. This is the most general case for the inclusion exclusion. That if there are n sets, the union of all those n sets, the number of elements in the union of all those is just by taking one at a time individually and adding their cardinalities, then deducting, taking two at a time and intersecting them, those two must be distinct. So I don't, here I is not equal to j, I, which by this I means that AI and AJ are distinct. Okay, if AI and AJ are same, then that's not different sets. Okay, similarly after this, I guess you got it. It will be taking three at a time. You add back. See what first it is some plus then minus then plus then minus alternately. It is going alternate. So you will taking three at a time. So we will just sum the cardinalities taking AI intersection AJ intersection AK and IJK are all distinct. Okay. The next it will be subtraction because there was a plus here. Subtraction taking four at a time. Okay, you got it. This is how the inclusion exclusion principle goes. So this is the following a nice pattern. The thing is that how can I ensure that in this pattern each and every element is counted exactly once? How can I ensure that? I mean, this is the generalized version of the inclusion exclusion principle. I will just write dot dot dot, which means up to n is equal to summation of ai's, where I is equal to 1 to n, minus summation of intersection ai intersection aj, I is not equal to j. Here all I, j, k, l all belongs to 1 to n. Okay, they are from 1 to n only. I'm not writing this, but it is meaningless. Okay, so the next it will be taking 3 at a time. See, plus minus. Then with here it will be plus. Taking 3 at a time. Sorry, I'm writing here. Okay, the space is not. Taking 3 at a time. AI intersection AJ intersection AK. I is not equal to J is not equal to K. Okay, like this. The next it will be taking 4 at a time. There will be a here is a plus. There will be a minus. Okay. See here plus minus like this. They will taking 4 at a time like this. Now I will tell why this actually works. I mean, how can we ensure that each and every element is counted exactly once here? So let's just assume that x belongs to this union. This is a set, and let x belongs to this set. Okay. Now I assume that x belongs to not, or if we take x belongs to all of n, then that will be a special case. Or if x belongs to one of ai, then it will be also special case. For generalization, I will take x to belong in some of the AIs, not all, some. Say let x belongs to some k of n, some k of AIs, means it is belongs to only k sets, not all. So let x belongs to a1 intersection a2 intersection up to ak. Means x is only present in a1 a2 up to ak, and nowhere else, where k is less than n, of course, less than equal to n. Now the thing is, you don't have to take 1 to k like this in order. You can take any k sets from any randomly. You can take any arbitrary k sets from 1 to n, like a1 a3 a7 whatever. But there must be only k sets. I took x belongs to only k of those n cells. Okay, it's not present in all. So I am going to prove that this x is counted here in the RHS exactly once. Okay, that is the main theme of the inclusion exclusion principle. Everything should be counted exactly once. So here, how many times it is counted here? Here, see, here it is. If AI belongs to this AI A1 to AK, then will be discounted. Otherwise, it is not. So there here it is counted k choose one times, right? Why k choose one time? From because it is counted because this is what a1 cardinality of a1 plus cardinality of a2 plus cardinality of a3 plus cardinality up to an. So in only in k of those will be present, right? So it is counted k choose one times here. You will get a better picture for this second one. How many times it is deducted? This element is deducted how many times? See, it is not present. It will only be present in AI intersection AJ, if AI and AJ belongs to this, right? Both belong to this A1 to AK. So and see, I and J are distinct, right? You cannot take same. So how many times it will be occurring? If it occurring K choose two times. Again, you are getting right this why this is K choose two, because see, among AI and AJ, upon AI and AJ, both will belong to this A1 to AK. Okay. AI and AJ both must belong to A1 to AK. And AI and AJ are distinct. So how many ways we can do that? K choose two ways. Similarly, here it will be K choose three ways. It is added back. Then it is subtracted K choose four times. Up to you get the idea. I am not putting the sign. But it will be K choose K. It will run up to K choose K. Okay. And I don't know what is the sign of this K choose K. It depends upon the parity of K. If K is odd, this will be plus. If K is even, then it's minus. I can write in a fancy way minus 1 to the power K plus 1 or something like that. But let's keep it like this. Okay. We don't want to go into those. Yeah, I can write that minus 1 to the power K or something. But it is okay. So according to inclusion exclusion principle, what is inclusion exclusion principle saying? It is saying that this must be equal to 1. Because why? Remember the old thing which I told, that each and every element must be counted exactly once. So this is the number of times this is counted. And the inclusion exclusion principle holds true if this is 1. If this is not 1, then I will just write a paper and tell the inclusion exclusion principle is wrong and give it to the mathematical community, and they will just say that yeah, my proof is correct. But mathematicians are not dummies. They know this will be 1. So that's why this works. So let's prove now. So we just said that the inclusion is any arbitrary element x which belongs to some k of those AIs will be counted this many times, and according to inclusion exclusion principle, this is 1. Remember here k is anything, any arbitrary natural number. Okay, k is any arbitrary natural number according to this. So the inclusion exclusion principle takes help of this, is saying that this is an identity. So let's prove. So our final proof is to show that this is always 1, no matter what the value of k is. Now, so our result is this. We have to prove this. If this is proved, then we are done. The inclusion principle is demystified. So I will show two different proofs. The first one is for mathematicians. Actually, yeah. I will use the binomial theorem. 1 minus 1 whole to the power k. If we expand this, you will get this only, and this is equal to 0. Okay. If you expand this, you will get this, and this way I can solve this. I can prove this. But for those who don't know binomial theorem, okay, no fear. I'm going to show it another way, which is more like a common sense way to prove. See what is actually saying this. Can I write 1 is equal to k choose 0? Yeah. 1 is k choose 0. So I'm going to rub this 1 and say that this is equal to k choose 0. Now if we shift those minuses in the RHS, I will get k choose 1 plus k choose 3 plus k choose 5 up to that is equal to k choose 0 was already here plus k choose 2. I shifted k choose 2 this side because this was negative sign here plus k choose 4 plus that. So this is equivalent to this. This is equivalent to this. So if I prove this, we are proving the same thing only. Now, what is this actually telling? Yeah, this looks like a combinatorial problem, but we're going to use common sense. This is saying, what is k choose? See, all these here, these are odd numbers in the LHS. K choose 1, k choose 3, k choose 5, the next order, like this. Here, in the RHS, everything are even numbers. So what is this equation telling? This combinatorial equation is telling that no matter what the value k is, the number of ways we can choose odd number of elements from a finite collection is same as the number of ways we can choose even number of elements from the same finite collection. I repeat slowly. For any given collection, any given finite collection, the number of ways we can select odd number of elements out of those finite collections is same as the number of ways we can select even number of elements from the same finite collection. Because this is what it says. So this is no longer a combinatorial problem. This is actually a problem on parity. So you all guess what I will use to solve this problem. I will use parity to solve this problem. Before going further, I'm going to highlight these points. I know this, you all know this stuff, but still I'm going to highlight odd plus odd is equal to even, odd plus even is equal to odd, and even plus even is equal to even. Okay, this is not zero, this is odd. Okay, odd number plus odd number equal to even number. I'm highlighting these because I am going to use these facts only to prove this one. So let's now see how to go forward. We have to prove the number of ways there are odd subsets. I mean by odd subset I mean the number of elements in the set is odd. That is called a odd set. Okay. So the number of the so I can also reframe this statement as the number of odd subsets is equal to number of even subsets for any finite collection. Okay. So how we can do this? First, I want to form a subset. So I select something. If you want to form a subset, I have to select something, right? So if I select something out of those k elements, then I must also reject something. I must reject the rest. So select plus reject is equal to k. You all got it? I am selecting something out of k elements. I'm selecting something. That means I must be rejecting something, right? So select plus reject is equal to k. At first, I assume that k is odd. I'm going to deal with the even case later. Let's assume first there are two cases, right? K is either odd or even. Let's assume first that k is odd. Now, if I select odd number of elements, then the remaining will be even number of elements, right? Because what I told that odd plus even is equal to odd, right? If this was also odd, then k would have been even, but which is not. We assume k is odd. So odd, if we are selecting odd number of elements, we are rejecting even number of elements. See, if we are selecting odd number of elements, these selection from the subset, and this what we rejected, those also from the subset. So this is an odd subset, right? Because we have selected odd number of elements, and this is an even subset, right? Because this contains an even number of elements. See, selection and rejection goes hand in hand. We cannot avoid one by doing the other. These goes simultaneously. So if there are odd number of elements, then there must be corresponding some even number of elements which we rejected. So odd subsets and even subsets are formed hand in hand. Hence, we showed that the number of odd subsets is equal to the number of even subsets for k if k is odd. If the number of elements in the set is odd, the number of odd subsets and number of even subsets are the same, which is proved. Now, what about even? If k is even, now I'm going to deal with the even case. What if k is even? If k is even, then if we select odd number of elements, then we are also rejecting odd number of elements because odd plus odd will only make even. So we are not forming an odd subset and an even subset hand in hand simultaneously. And seems like we are at a loss. We can't apply the same logic here. But the thing is that even it seems like we cannot apply the previous logic here, but that is actually an illusion. We're going to apply the previous thing which we already know, which we already proved only, but with some manipulation. What is the manipulation? See, if k was odd, then we would have been happy because then it's done. Since k is even, we can't do anything. Fine. How to make this odd? We can't add anything and make it odd. We can add, but that will just change the whole thing. Okay. That would have been also worked. We can add something. We can add something here and make it odd, or we can take out something and make it odd. You can prefer either way, but I'm going to take out something. Let's remove one particular element from this element set and name that element A. So here, if initially there were k elements and we removed one element, so it will be k minus one element here now, which will be odd because initially k was even, so k minus one will be odd. So now we can apply the previous logic that, see, these are all the subsets of this new set which we formed by taking out A from the set. I'm writing these these are the subsets these are the odd subsets of k minus one element, and these are the even subsets of k minus one elements. This is a box. But in all these subsets, we don't have A here. So these are not all the subsets of K. So what to do now? But these are all equal, right? The number of odd subsets in this and these are equal. We already showed in previous way because odd subset and even subsets go hand in hand if K is odd. Here K minus one is odd. So now suppose this is an odd subset. Now we're going to this. We only showed that if A is not present, then the number of odd subsets and even subsets are equal. Okay. Now what if A is present? We add A back into all these subsets. See, these are the subsets which does not contain A at all. These don't have A. we have taken data, but the number of odd subsets which does not contain A is equal to number of even subsets which does not contain A. Now we add A to all of those subsets, each and every odd or even subset, doesn't matter, everything. What will happen? Those odd subsets will turn into even subset because we are adding one element to each of the subsets. Since initially there were odd number of elements, if we add one element to each of them, the cardinality of each of them will be even. So I'm writing E subscript A. This means that A is present in A. Okay. A is present in this subset, in all these subsets. And similarly, these will switch to odd subsets because we have added A to these only. Okay. Since initially these two were equal, the number of odd subsets and number of even subsets were equal, and we just added A to all these. So all these four things will be equal. This is what number of odd subsets which does not contain A, number of even subsets which does not contain A, number of even subsets which contain A, and number of odd subsets which contain A. All these four things were equal. So the number of even subs, these are the number of even subsets of the original set containing A and containing and not containing A. And these two are all the subsets of the whole set which contains k elements. These are the odd subs. All these four are equal. So hence we proved that it doesn't matter whether k is odd or even. The number of odd subsets and number of even subsets of any finite collection is always the same. Always. Of course, k has to be a natural number. I mean, 0 is a natural number. If there is nothing, then this is not true because we can only form one, only 0, the null set. A null set means even. So that's not going to work. If k is a natural number and that is positive integers, then this will number of even subsets and number of odd subsets will always be equal. And this is the gist of the inclusion exclusion principle. That is why no matter what you do, this minus and we are sometimes we are just alternately adding and subtracting. That is because it will always result in one, as the number of odd subsets and number of even subsets in any finite collection is always the same. So I hope these common sense way is also logical. So that's all for in this video. Thank you for watching this. Bye bye.